Good morning. Myself, Dr. G. Venkat Subbareddy, Associate Professor of EEE Department. Today we are going to discuss about black diagrams and signal flow graphs in control system. First of all, what is the black diagram? The entire system can be represented in a single block, that is known as a black diagram. It should be shorted or symbolic or pictorial representation relating between the input and output of a physical system is known as a black diagram. Black diagram has a one input signal and one output signal. Mathematically, the output is equal to 3s into x. That is nothing but a x of s is nothing but input signal, y of x is nothing but output signal. The system gain is nothing but 3s. The mathematical output y of s is equal to 3s into x of s. The value of the input is multiplied the value of the block gain and get the output. That is input and output relationship. The overall transfer function is obtained from the ratio of output to input. Need a black diagram. It is not convenient to derive a complete transfer function from complex control system using differential equation method. Black diagram is a simple way to represent any practical complicated system. In each component of a system is represented by a separate block is known as a functional block. These blocks are interconnected in proper sequence based on its mathematical relationship. That is nothing but a necessity of black diagram. The summing point. In case of block diagram, some components are summing point, take-off point, and blocks are connected in series, blocks are connected in parallel. There are some rules for reduction of block diagram to obtain the simplified transfer function. The summing point. Two or more signal can be added or subtracted at a summing point. Then here three signals x, y and z. X is a positive signal, y is a positive signal, z is nothing but a negative feedback signal, then output is equal to x plus y minus z. That is nothing but a summing point is represented as a in this way. The take-off point. The output signal can be applied two or more points from take-off point. The signals is taken from the two or more points is known as a take-off point. Forward path. The direction of flow of a signal from input to output is known as a forward path. The direction of flow of a signal from output to input is known as a feedback. This is nothing but a simple block diagram with a negative feedback system. Forward path is nothing but the input to output. Feedback is output to input. One first rule is, while reduction of block diagram, first rule is for blocks are cascade. The gain of the blocks is connected in cascade and gets multiplied with each other, multiplied from each other. R of s is nothing but input signal, C of s is nothing but output signal. The output by input is equal to G1, G2. When the blocks are connected in series, in cascade, then the resultant will be the product of the two gains. This is a one rule for a blocks are connected in cascade. This is one example. G1, G2, G3, three blocks are connected in cascade, then the total gain is nothing but G1, G2, G3. This is a simplified block. When take-off point after G2, then find the equivalent. The first one is G1, G2, G3 is not correct because of take-off point after the block of G2, then the second one is nothing but R of s is equal to G1, G2, and R1 is another take-off point and G3, that is a correct. Block diagram reduction, this can be important. The second rule, the blocks are connected in parallel. Gain of the blocks is connected in parallel gets added algebraically. When then forward path G1, G2, G3, three blocks are in forward path, then the resultant is nothing but G1 minus G2 plus G3, because the second one is nothing but minus sign. Then G1, G2 minus G3. Then transfer function C of s divided by R of s is equal to G1 minus G2 plus G3. See, one more rule, elimination of feedback loop. This is a very simple in case of we already discussed in closed loop control system. to find out the overall transfer function of a simple closed loop control system. G of is nothing but a forward path, H of is nothing but a feedback. Then here a positive gain, then the negative feedback, then denominator will be positive, then for positive feedback in the denominator will be negative. Then C of s divided by R of s is nothing but G of s divided by 1 plus or minus G into H in general. That is nothing but in case of a negative feedback system, in the denominator is positive sign, in the positive feedback system, in the denominator is negative sign. C of s divided by R of s is nothing but a overall transfer function that can be represented as G divided by 1 plus or minus G into H. This is a most important rule we used in block diagram reduction technique. The third rule is elimination of feedback loop. That is a small derivation how to get in case of elimination of feedback, then we get G of s plus 1 plus G of s into H of s. G of s is nothing but the forward path, H is nothing but a feedback signal or sensor. Then we derive the expression, the transfer function C of s divided by R of s is equal to G divided by 1 plus G into H. E of s is nothing but error signal, which is the difference between reference input signal and feedback of B of signal. Then C of s is equal to error signal into gain of G. Then we get finally the find out the transfer function from C of s divided by R of s is equal to G divided by 1 plus GH. In case of positive feedback, then the only change in the denominator. Positive feedback, C of s divided by R of s is equal to G divided by 1 minus G into H. That is nothing but a positive feedback system. Next, another rule, shift a takeoff point before the block. If you want to shift this takeoff point before the block G, then one more gain G can be added in the before the block. This is a rule. The R of s in the first diagram, R of s into G of s is equal to C of s output. In the second diagram is also x is equal to G into R of s. Shift takeoff point before the block. Next rule is shift takeoff point after the block. When the takeoff point is shifted after the block, then G becomes 1 by G added in the before the block of X. This is another rule. Shift the takeoff point after the block, we get 1 by G. Shift the takeoff point before the plot, we added the G. This is another rule for reduction of block diagram technique. Shifting a summing point before the block. If summing point is shifted before the block, then 1 by Z added in the feedback. Then G of s is equal to R of s into G plus into X. Then final both are, the output will be same. This is a one more rule. That is shifting sum of point before the block. Then we get 1 by Z in the feedback. Next, shifting the summing point after the block. If summing point is shifted after the block, one more G is added in the feedback. This is another rule, shifting the summing point after the block. This is a one more rule. Associative law of summing point. In order to summing point can be interchanged if two or more summing point that is connected in series. If we want to required, then shifted two summing point whenever the necessary for simplification of block diagram technique. Ordinarily, we can split the summing point into two summing points and summing another order. If we want three signals is added in at one point, then we shift in the summing point into two summing points, plus plus and plus minus. This is another rule for reduction of block diagram. Then more the signals is added in the summing point can be shifted into two summing points, added two signals. The same with the same sign. Block diagram majorly we follow these rules. We are solving the block diagram to get a single block equivalent. The said rule is needed to be applied. After each simplification, a decision needs to be taken. For each decision, we suggest performance to reduce in the following order. The first point is eliminate the series blocks. First of all, connected series block, that is nothing but a cascading. First rule is eliminated series block. Then after that, eliminated in parallel blocks. Then finally, we get eliminated feedback. We follow this rule, it is easy to simplify the entire block diagram into single block. In the block diagram search in blocks having First preference rule 1 for series, second preference rule 2 for parallel, third preference rule 3 for feedback. The choice how to reduction of block diagrams in this order. Fourth or fifth rule, shifting the takeoff point before and after the block, and sixth or seventh rule, shifting the summing point before and after for finally adjusting the summing point. Second choice. No possible combination of series and parallel or feedback loop, then go for another rules. So after getting all these rules, once again we discuss about all these rules. The first rule is nothing but blocks are connected in series, cascade, then G1, G2, G3. The second rule is blocks are connected in parallel. The resultant block is G1 plus G2 plus G3 or G1 minus G2 plus G3. The third rule is elimination of negative feedback or positive feedback, D divided by 1 plus GS. Fourth rule also elimination of feedback. Then shifting the takeoff point before the block. And another one is shift up the takeoff point after the block. Then shift the summing point before the block, then shift the summing point after the block, and associate up two blocks, interchanging up two blocks, and split the summing point into two summing point. By using these 9 rules, we solve the problems. For example, we consider a simple problem to solve by using the block diagram reduction technique. R of S is nothing but input signal, C of S is nothing but a output signal. The first rule is nothing but cascade. There is no cascade elements. Then G1, G3, G5 are connected in parallel. First to simplify, G5, G3, G4 both are connected in parallel. Then resultant block is G3 plus G4 plus G5 into G2. The second one is series in G2. We cannot use, there is a no intermediate series block, hence the rule 2 is applied. G4, G3, G5 are parallel. We get the equivalent of G3 plus G4 plus G5. First simplify this one. Then added to G2, these two are connected in series, then G2 into G3 plus G4 plus G5. The second rule, series are series block. G2 into G3. The elimination of feedback, G1 and H1. To eliminate this one, then we get G1 divided by 1 plus G1 into H2. These two are connected in series, then we get series block. Finally, you apply the feedback loop, then finally you get the transfer function, then series with G6. This is a final transfer function of the given block diagram by using the reduction techniques. This is a one problem how to solve this blocks. For another example, hence the overall transfer function C of S divided by R of S is equal to G1, G2, G6 into G3 plus G4 plus G5, then 1 plus G1 H1 plus G1 G2 H2 into G3 plus G4 plus G. It is nothing but a one transfer function of a given block. Next, one more problem. The second problem to reduction of block diagram by using block diagram reduction techniques. G3 and G4 both are connected in series, then G3 plus G4 is then parallel G3 plus G4, and another is eliminating the inner loop. G2, G3 is a forward path, H1 is a feedback, then eliminate this one, then finally added these two cascade. G2, G3 is nothing but series, G3, G4 is nothing but a parallel, then the feedback, another elimination of feedback, then finally is multiplied these two blocks, G1, G2, G3 plus G4 divided by 1 plus G1, G2, H1 in the feedback of H2, then overall transfer function C of S divided by R of S is nothing but a overall transfer function. Second block. Then by applying these rules, we find out the total transfer function of a given block diagram, reduction of block. The following steps is reduced in block diagram which have the many blocks, summing points and takeoff points. Check the blocks are connected in series, then simplify. Check the blocks are connected in parallel, then simplify. Check the blocks are connected in feedback loop and simplify. If there is any difficulty, takeoff point while simplifying, it shift towards the right or left. If there is any difficulty, the summing point, while simplify the summing point towards the left or right, then repeat the above step till we get the simplified single block. These are the main rules to follow the rules while simplifying the block diagram. Then find out the transfer function by using summing and takeoff point. by internal loop. Eliminate the internal feedback G2H1, then G2 divided by 1 plus G2H1. To eliminate, apply the rule 1 for elimination of inner feedback. Then the three are connected in cascade. Then simplify this 3, the second rule. G1, G2, G3 divided by 1 plus G2H. After that, the forward path. Both are in forward path. G5 and the black are G1, G2, G3 divided by 1 plus G2H1. These two are connected in forward path. Then after that, G4 is cascade. Then added the G4 into G4. G4 into G5 plus G1, G2, G3 divided by 1 plus G2H1. Then eliminate the feedback. Then we get the overall transfer function of a given signal flow graph. This is nothing but a overall transfer function of a given signal flow, given block diagram. This is another problem. Then find out the, then we apply the rules by simplify the block diagram. Determine the transfer function in 3 ways. By using the differential equation and Laplace transform, the another one is a block diagram reduction technique, or third one is a by reducing the signal flow graph by using the Moissan gain formula. Signal flow graph. That is a one concept to determine the overall transfer function by reducing the block diagram by applying the block diagram reduction techniques. Another way of finding the transfer function, that is nothing but a signal flow graphs. The alternative method of block diagram representation developed by Samuel Joffer Mawson. A signal flow graph consists of a network in which the nodes are connected by directed by the branches. It displays the flow of signal from one point of a system to another and gives the relationship among the input and output signals. That is nothing but a signal flow graph. How to represent this electrical signal is converted into signal flow graph. Write inner loop equation V1 of S is equal to 1 by Cs into I1 of S into R into I1 of S. The another equation at the output, voltage across the resistor V2 of S is equal to I1 of S into R. Then Cs into V1 of S minus Cs into V2 of S is equal to I1 of S, that can be represented in blocks. V1 of S is nothing but input signal, first signal. V2 of S is nothing but output signal. Then I1 of S is equal to V1 of S into Cs is equal to I1 of S. I1 of S into R1 minus C1 is equal to V2 of S. This is nothing but by given equation that can be represented as a signal flow graph. 3 nodes are taken. One is nothing but input of signal V1 of S. The second one is a current I1 of S. The third one is a V2 of S. I1 of S is equal to Cs into V1 of S and minus Cs into V2 of S is equal to I1 of S. I1 of S into R is equal to V2 of S. Then that equation, then that electrical network can be represented by a signal flow graph taking the 3 nodes. That 3 nodes in nothing but one is the input voltage, then a loop current, another one is a output voltage. Consider a simple equation below to draw a signal flow graph y is equal to ax. X is nothing but input signal, y is nothing but output signal, a is nothing but a transmittance. Then that can be represented as a signal flow graph x and y. The arrow mark indicated the direction of flow of a signal, that a is nothing but a gain, that can be represented at the top of the straight line or top of the variable. That can be represented as a signal flow graph. Consider a simple equation y is equal to ax that can be represented as a signal flow graph of the equation x is input, a into x is equal to y. Every variable in signal flow graph is designed as a node. Every transfer function of a signal flow graph is designed as a branch. Branch is always unidirectional. The arrow of the branch denoted the direction of the flow of a signal. The direction of a signal flow. Terminology. A input node or a source contains only outgoing branches. The input, this is a definitions. What are the input node? What are the output node? What are the path, feedback, path, forward path and feedback? We know that all these definitions. What is the input node? An input node or a source is contain only outgoing branches. That is nothing but x1 in the graph. That is nothing but input. Only outgoing sources. Output node is nothing but a sink. It contains only incoming branches. That is nothing but a x4 is nothing but a output node. that is only coming up a input signal. There is no output signal, that is not the output. A path is a continuous or unidirectional section of the branch along which no node is passed more than once. X1 to X2, X2 to X3, X2 to X4. That is nothing but a forward path. Forward path. The signal is starting from the source node and terminate at sink node. The no node is encountered twice. That is nothing but a forward path. Feedback path. Feedback loop is a path which originate and terminate the same node. That is nothing but X1 to X2 to X3 and back to X3 is a feedback path. The same node. The branch is started at same node and terminated at the same node through a no node is encountered twice. That is nothing but a feedback path. Self loop. A feedback path consists of a single loop. Then A33 is nothing but a self loop in this graph. A33 is nothing but a self loop. The gain of the branch is a transmission function of that branch. Gain is a branch of transmission of function at this branch. The path gain, the product of branches gain encountered in traversing the path, the forward path X1 to X2, X2 to X3, X3 to X4, then A21, A232 and 32 is nothing but a forward path gain. And loop gain, the product of the branch gain of a loop, the loop gain of the feedback from X2 to X3 and back to X2, that is nothing but A32 and A23. These are some important definition while finding the overall transfer function by using a signal flow graph by using Moss and gain formula. Then non-touching loops. The two loops path or a loop or path or a loop and a path is said to be non-touching if they have a no nodes is common. No nodes is common. Suppose for a algebraic equation can be represented as a signal flow graph. The first one is x1 into a into x0, b into x1 plus c is to x1. X1 is an output signal. The signal is coming from towards the x1 from x0, x2 and x1 and x2. The second algebraic equation x2 is equal to dx1 plus ex3, then signal from towards the x2 from x1 with gain is d, towards x2 from x3 gain is e. X3 is equal to fx0 plus gx2, the signal coming from x0 to x3 and signal coming from x2 to x3, the gains are f comma j. X4, the signal coming from x3 to x4 is nothing but a h, that is nothing but a signal. This can be represented as a signal flow graph. The algebraic equations can be represented as a signal flow graph by using this one. Moss and gain formula. The block diagram reduction technique requires successive application of fundamental relationship in order to arrive the system transfer function. On other hand, Moss-Son's rules, Moss and gain formula for reducing the signal flow graph to a single transfer function requires the application of one formula. The formula was developed by S.A. Moss-Son when he related to the signal flow graph and simulate the equation that can be written from the graph. The Moss and gain formula is nothing but C of s divided by R of s is equal to sigma k is equal to 1 to n pk into delta k divided by delta. Delta is nothing but a determinant, pk is nothing but a number of forward path. Pk is nothing but a k forward path, p1 ante the p1 is nothing but first forward path, p2 is nothing but second forward path. Like C of s divided by R of s is equal to k is equal to 1 sigma pk delta k divided by delta. Delta is nothing but a determinant of the graph. Delta can be defined as 1 minus sum of the loop gains of all individual loops. Then the second is a plus sum of loop gains of all possible combination of pairs of two non-touching loop minus sum of the loop gains all the possible combination pairs of three non-touching loop plus sum of the loop gains of all possible combination of four non-touching loops, like this. That is nothing but delta. Delta is nothing but a determinant of graph. Delta k is the same as that of a delta by the loop non-touching to the k forward path. This is a very important formula to determine the overall transfer function from the signal flow graph by using Moss and gain formula. This is one more method to find out the total transfer function. One is nothing but a block diagram reduction techniques. Another simple way is nothing but by using Moss and gain formula. Procedure to derive the transfer function from the signal flow graph. Find the number of forward paths. How many forward paths are present in the given graph? To identify the first number of forward path. Calculate the forward path gain pk for each forward path of k. Identify the individual loops. How many individual loops are present in this graph? Identify the pair of two non-touching loop and identify the pair of three non-touching loop. Similarly, etc. If you have any four non-touching like that. Calculate the delta in step 2, step 2, 3, 4 and 5. Calculate delta k, the portion of delta but non-touching the forward path of gain. Applying all above data in Moissan gain formula to get overall transfer function of a given signal flow graph. A simple signal flow graph to find out the overall transfer function. There are two forward paths. First, identify how many forward paths are present in this graph. There are two forward paths. One is nothing but G1, G2, G1, G2, G4. That is a one forward path. The another forward path is G1, G4 and G3. G1, G4 and G3. There are two forward paths. Then C of S, CF by R is equal to P1 delta 1 plus P2 delta 2 divided by overall delta. Delta is nothing but determinant gap. There are three feedback loops, individual groups. L1 is nothing but G1, G2 into H1 ఒకటి. L2 is nothing but minus G1, G2 minus G1, G2, G4 into H2. The third loop is minus G1, G3, G4 into H2. This is another loop. Then three individual loops. There is no non-touching loop, therefore delta is equal to 1 minus sum of individual loop gains of all the loops. Delta is equal to 1 minus L1 plus L2 plus L3, 1 minus G1, G1, G4, H1 minus G1, G2, G4, H2 minus G1, G3, H2 into that is nothing but delta is nothing but a overall delta determinant of the graph. Delta is nothing but a determinant of the graph. Elimination part 1, delta 1 is equal to 1 minus sum of individual loop gain, like that there is no individual loop non-touching of loop 1, then delta 1 is equal to 1, and path gain delta 2 is equal to 1 minus sum of individual loop gains plus dash dash, delta 2 is also 1, all the loops are touching this forward path also, then delta 1 is equal to 1 and delta 2 is equal to 1. Then finally the overall transfer function C by R is equal to P1 delta 1 plus P2 delta 2 divided by delta, then go to overall transfer function by using signal flow graph. By using signal flow graph, this is a very simple method as compared to the block diagram reduction techniques. The another problem, by applying the Moissan gain formula to apply the overall transfer function of the system represented by the following signal flow graph. In this problem, there are a forward path of each forward path. There is P1 and P2. There are two forward paths. G1, G2, G3, G4, that is a path 1. G5, G6, G7, G8, that is nothing but a path. Calculate all individual loops. L1, G1, H2, L2, H3, G3, and L3, G6, S4, L4, G7. There are four individual loops, non-touching loops. L1, L3 is non-touching loop. L1, L4 is a non-touching loop. L2, L4 is non-touching loop. L2 and L3 is non-touching loop. Consider three non-touching loops is none. Then delta is equal to 1 minus L1, L2, L3, L4 plus L1, L3 plus L2, L4, that is the non-touching loops. Then find out the delta 1 minus of three individual loops plus 4 non-touching loop for callable of non-touching. Delta 1 is equal to 1 minus L3, L4, 1 minus L3, L4, and delta 1 is equal to 1 minus L3 and G6, S6, L4 and G7, S7. Eliminating our forward path, delta 2 is equal to 1 minus L2, L3, 1 minus G2, H2 plus G3, H3. Then overall transfer function y of s divided by r of s is equal to P1 delta 1 plus P2 delta 2 divided by delta. Thank you.